Welcome back, everybody. I'm going to look at the two most important reactions in Chapter 7, starting with hydration of alkynes. Well, that covers both of them. One version is using oxymercuration, and I think that sounds familiar. This next word does not. Protonolysis, but it's a word that I can get my head around. It says use a proton to cut something apart. I like words like that. One, it's a portmanteau, and two, it means, every part means something. There's no people's names in there. All right. So the mercury we're using here compared to Chapter 6, let's just have a Chapter 6 comparison on the side here. Chapter 6, we reacted alkenes, and we used a two-step process with Oxymercuration. We used Hg that was different. It was still Hg2+, but there were two acetates on it. Then we had the water, which is the same. Okay, the mercury was mercury 2+, that's the same. But it's a mercury 2+ acetate this time, that's different. Water has to be in both, that's the same. And in Chapter 6, we got rid of the mercury with a separate chemical. And we're getting rid of the mercury with a different process entirely in Chapter 7. So Chapter 6, you created this. And sadly, water may be green for contrast, because that's where your OH comes from. And mercury on the other carbon gets replaced by hydrogen in step 2. All right, that was Chapter 6. A lot of similarities. First step in the mechanism in Chapter 6 was to ionize one of the acetates off of the mercury. And fortunately, in Chapter 7, I've already got it ionized for you, so you don't have to break it apart to 2 ions. I've got the ions for you. And the next step in Chapter 6 was to attack the mercury cation with the pi electrons. Mercury is a piophile, loves pi. And it loves making partial triangles. This triangle is different than the one on the previous page. Please know that. Don't throw points away. Makes me sad, makes you sad. So the pi is gone, almost. It is now a partial pi. And we also have 2 partial sigma bonds. These are partial bonds, not dashes. And the question is, you started with mercury 2+, please account for the 2 pluses here. Well, one of them's gone, and it's been moved to a position where it's shared by all 3 atoms in the ring, and the other's still owned entirely by the mercury. So the triangle's very similar. In Chapter 6, the triangle looked like this. It's always good to compare old with new. Mercury was only a 1+ on the mercury, and plus shared in the middle is here. That doesn't even look like a triangle. Anyway, I think you could make it out. Very similar mechanism. Okay, next step was to do, hey, you made a triangle. Every time you make a triangle, the next step is always what? Blank, blank attack. Yes, backside attack. Lone pair. Which carbon? Which carbon do you do the backside attack on? Same answer every time. More substituted carbon. Now, generally, I would have arrows. I mean, I don't even want to show them because you'll try them on a test, and you shouldn't show an arrow where this bond breaks. It's an arrow means 2 electrons, and there's not even 1 electron in that bond. So just Just have it implied that it breaks by the fact that you're drawing this product right here. Pi bonds here. It attacked from the left. The water attacked from the left. So it's on the left. Mercury was on the right and it stays on the right, but now all the electrons in those partial bonds are there in a real bond. That's a real bond. 2 electrons, old school. Where's this isopropyl group? Well, the isopropyl group got pushed over with the backside attack. Yours doesn't have to look that pretty. All I need to see is the O on the opposite side of the pi bond as the mercury. Then I'm happy. Okay, we have an oxonium. In chapter 6, what did you do with the oxonium? You neutralized it. It is a strong acid. It needs neutralizing. The question now is, what's our strongest base available? Is it water or is it sulfate? We haven't used sulfate. And the answer is sulfate. We don't know a lot about the pKb of sulfate because we only know sulfuric acid, H2SO4. Its conjugate base is hydrogen sulfate with a pKb of 19. So sulfate's got to be a stronger base than that. But I didn't make you memorize the pKa of hydrogen sulfate. But its pKb of sulfate is stronger than that of water. You do need to know that. And I think we're going to venture over to the left here. Sulfate ion, what's a way we can draw it? Well, I need one of the O's to have a lone pair to grab the H. And the other one is just hanging around on the other side, SO3. Please verify that this is the same as this. It's just got a little more information. It's not like it came from nowhere is what I'm trying to say. Grab the H, neutralize, and you have an alcohol. It's a special alcohol. You don't know why it's special yet. Got a rogue electron over there. And it's attached to an alkene. Alkene has an isopropyl. And it has a mercury cation. We have to get rid of the mercury cation. There. Let me show you what it needs to become, and maybe you can tell me what you think happened. Let's use blue. It needs to become this. No changes there. No changes here. But there's a new hydrogen here. And the other thing you made is can you verify that you know there's a new hydrogen down here that wasn't here before? 4 bonds to carbon, 3 of them are showing, therefore 1 H is here. 4 bonds to carbon, 2 of them showing, therefore 2 bonds to H. There's a new H there. Where'd it come from? It came from this part of the name, and it came from, very surprisingly, sulfuric acid, which hasn't even reacted yet. That should be surprising to most. Sulfuric acid is a strong acid. It's one of the strongest acids we use. In fact, it is the strongest acid we use almost all of the semester. And we haven't reacted it until what, step 3? That's a testament to just how reactive the mercury 2+ cation is. It reacts ahead of a strong acid. Wow. Oh, didn't finish drawing out sulfuric acid. And this is protonolysis. I'll even write it over the arrow. Using a proton to bust off the mercury, lyse it off. Attack the proton. Sulfate ion is made. Let me show that up here. hydrogen sulfate if you want to be picky. And that's the three pieces you get from these two pieces reacting. And what do you call a reaction that started with, I want to see it, started with mercury 2 plus. We did all these steps to here, and we have mercury 2 plus back again. It's ready to go again. What do you call mercury 2 plus in this reaction? Yes, you do call it a catalyst. You don't have to show me the catalyst here. It's understood that it's coming off. But how do we make this into this? This is rather new and profound. What are all the changes? Isopropyl is attached to a carbon with a single bond to O. Isopropyl is attached to a carbon with two bonds to O. So we're gaining a bond to O. The old pi bond is now a new pi bond there. See? So a pi bond moved. What else moved? Well, this H is no longer up on the O, but there's a third H down here. We have two H's down there. So something's got to protonate the alkene, and something's got to deprotonate the alcohol. And when we have an alcohol attached to an alkene, it's a new functional group, and it deserves special attention, some fanfare. It's called an enol. It is a new functional group added to the 8 we studied earlier. It's not a normal alcohol. It has different behavior to an alcohol. It's an enol. It is what it says. It has an ene and an ol. And what happens in this last step has a very, very fancy name. Let's put that fancy name here. I can't get too fancy with the type of pen. It's called TAUTOM, tautomer. Tautomers are isomers where a pi bond has moved and a hydrogen atom has also moved. And this qualifies as a tautomer of this. The hydrogen moved from here to down here, and the pi bond moved from here to up there. And the process to make tautomers into, or interconvert them, between each other is called tautomerization. Isn't that the most righteous word you've heard all semester? And you need either an acid catalyst, which we're going to use here, or a base catalyst, which we're going to use in the next reaction. And the acid catalyst is sulfuric acid. And you're saying, wait, there's no sulfuric acid here. We used up sulfuric acid here. Well, we're going to make a sulfuric acid when we do this. Grab that H. And when we make it, we're going to use it. So I'm going to put it here. And here's the arrows for tautomerization. This will not be the last time we see it today, tomorrow, next week, next month. Ask my 242 students. They're doing tautomerizations they haven't seen before to this day. It is a process that is very common in organic chemistry. Look at those arrows. Impressive. I will describe the arrows. Sigma bond from the, lone pair from the base makes a sigma bond to the H. That's a nice acid-base reaction. The sigma here becomes a pi. That's what that arrow means. The old pi picks up a proton on the down carbon here from the sulfuric acid. So sulfuric acid is used, and then here we make sulfuric acid. Yes, sulfuric acid is a catalyst for this tautomerization. So there you have it. We're going to do another version of this before this day is over. And we're also going to do 2 versions of the next one. Just deciding, I think we'll do the next one before the break. And you might have guessed already that it's the hydroboration version, which will put the boron on a less substituted carbon because it's less electronegative than hydrogen. And then oxidation is going to replace the B with an OH. If you see that down here, where are you? Where are you? Where are you? Where are you? Oh, there. Oxidation puts an OH where you used to have the B right there. And that's an alcohol attached to an alkene. What do you call that? An enol. Enol. What do enols do? Either under basic conditions or acidic conditions. They undergo step 7 is called tautomerization. So here's what we're going to do. We're going to look at this mechanism before the break. And then after break, we're going to do a version of the oxymercuration one and this one. Good game plan. So let's just go over all the steps here. And I'll remind you all the patterns we saw last day. They're down here in the first 6 steps. It's the exact same mechanism as the hydroboration oxidation of alkenes is the same as alkynes, except you add a tautomerization at the end. So you better learn this one too. Hydroboration, both these new bonds happen at the same time. First arrow, pi attacks the more positive boron. Boron, electronegativity, 2.0. Hydrogen electronegativity, 2.1. Always attack the less electronegative atom because it feels more positive. I'll even put the little reminders up here. You don't have to put them on the test. There you go. And you get a syn addition. This is not BH3 like we saw in chapter 6. We used HBHH. In chapter 7, we switch it to a boron that's got bulky R groups. That's branched groups. Branched where they're attached is bulky. And the name of the group is sec isopentyl. And my lab students will tell you another way to say sec isopentyl is to say sec isoamyl. It's both secondary and iso. You can draw it. Look at the text if you have trouble. And there's a discussion in the textbook about why we can't just use BH3 like we did in chapter 6. There's issues with alkynes being a little more reactive that make that a bad choice in chapter 7. And the good news is you don't have to worry about the reaction happening 3 times. That can only happen once with one H. And why are the new groups on the same side of the alkene? Why are they syn to each other? The answer is both of these bonds happened at the same time. There was no triangle. There was no backside attack. Therefore, both at the same time gives syn. Moving on, after you got the boron on there, you oxidize it down to an O. And then the O is going to undergo tautomerizations. All the steps are 1, 2, 3, 4, 5, 6, 7. 1 and 6 are both acid-base. That sound familiar? I hope it does. Acid-base were the exact 2 chemicals in chapter 6, hydroxide and hydrogen peroxide. Then they generate a peroxide anion. Both times you generate an O- anion, it attacks the boron here and here. That's an O- that was generated in this step. Okay, so step 1, acid-base. Step 2, the O- generated in the acid-base step attacks the boron. Boron goes from, I know I put a partial charge up here, but it really has, its formal charge is 0, goes 0, -1, 0, -1, 0. So that follows the chapter 6 pattern that we saw. After making a 4th bond, boron is negative. This is the rearrangement step of the carbon group from bonding to boron to the stronger bond to oxygen. And more importantly, you're breaking an OO bond, getting rid of these lone pair repulsions, which are talked about here. You're generating an O minus. Both times you've generated O minus, it's attacked the B, making a fourth bond, making B an anion. So we put one O minus onto the B and we take the other O minus off in the next step. And remember, steps 1 and 6 are both acid base. The O minus you generated here takes a proton from HO boron with 2 R groups. Acid base over. You've generated an enol. Enols undergo tautomerization with an acid-base conjugate pair, whether you're starting with a strong base and a weak acid, or a strong acid and a weak base. The mechanisms are identical. The base takes the H from the alcohol portion of the enol. The sigma between the H and the O becomes a pi, carbonyl. The old pi picks up a proton from the acid, the conjugate acid of the base. I will say the same words over again. The base takes the H from the alcohol of the enol. The sigma becomes a pi. The old pi picks up a proton from the conjugate acid of the alcohol of the base, of the base. And you generate a carbonyl, in this case, an aldehyde. Why aldehyde and not ketone this time? It's because you put the B on the end and the B gets replaced by an O. So what you're going to do, we're going to go to break real soon. Screen capture this and you can work on it over the break. We're going to do both the reactions. So this one, I'm going to leave some room for you to practice at home. And we're going to start off by doing the oxymercuration / protonolysis to generate a ketone. And then the next one, we're going to do hydroboration with sec-isoamyl borane, followed by oxidation, yielding an enol, which tautomerizes to an aldehyde here. So you've screen captured that, because in 5, 4, 3, 2, 1, we're going to break. See you on the other side.